Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel. Hello, folks, and welcome you back to the third episode of our crash physics course. Now, in this third episode, we are going to be dealing with work, energy, and power. Let us start by understanding what work actually means. Work is said to be done whenever a force moves the point of its application a distance in the direction of the force. Now, what this means is that work is whenever you have a force and then you move an object a distance. So that force must be applied on that same object. So if I push a trolley now and that trolley moves a particular distance, the work done is the product of the force which I used to push and the distance the trolley moved in response to my force. Now that means work is the product of force times distance. Now work is also defined as the product of the force and the displacement in the direction of the force. Now the reason because of this is that if you try pushing the trolley forward and actually the trolley moves backward, you have negative work. So because that displacement has directions, so that means the work is the product of the force and the displacement. So when the displacement is in the direction of the force, is a positive work done. Now, in order for us to understand the concept of work, I want us to imagine a man moving or climbing up a flight of stairs. Now, as he's climbing up, his height is increasing. That means the distance moved, the vertical distance moved, and also he's doing work because he's applying some force by his muscles and is acquiring a distance move, which is the vertical distance. Now, distance, it doesn't have to be horizontal; it can also be vertical. When you raise a ball from the floor up to your head, now that is also distance. That's vertical distance. Now you should know that this work done, it also is the product of the force. But what's the force applied? The force is actually the weight of the man. That means the weight of the man is the force which has to be moved upward. So the force is the weight, and the weight is equal to the product of the mass times acceleration, which we've talked about in the previous episode, and also which is a basic concept in physics. Now that is the product of the mass acceleration gives the force. Now if you want to look for the work, you look for the product of the force and the distance, which is the height. So that means the work is the force, which is mg, and multiplied by the height, which is h. So our work is mgh in this case. Now there's a case similar to the previous case we had. So in this case we are talking about falling bodies. Now, but before I forget, the previous case we were talking about the man climbing up the stairs, and that work done is potential work. We will go to energy soon, but now this case of falling bodies, when a body falls freely in a force field, for example, I mentioned earlier that on our Earth we have a gravitational force, and that force produces some gravitational work, which is done when we try to escape from the force of gravity. The gravitational force brings us back, and that results in the gravitational work. Though it must be clear that actually we are the one who actually starts that process, because when you try to go up, you are exerting some work. So that work causes a kind of imbalance. So and then the gravitational force also does work to balance that your force out. It's all about action and reaction, and we're going to be talking about it in a subsequent video of this course. But moving on, now this in gravitational field, the work done is equal to the product of the weight of the object, which is the force due to gravity, and then multiplied by the height, the displacement of the object. So now that is what we'll talk about here. Now here's an example that perfectly illustrates the concept. So in this example, we have that a loaded sack of total mass 100 kilograms falls down from the floor of a lorry 2 meter high. Calculate the work done by gravity on the load. Now we mentioned earlier that the gravitational work is equal to the product of the weight and the height, right? So the work is equal to the weight mg times height, which is mgh. The work is mgh. That's equals to the m is 100 kilograms. The g, which is the gravitational acceleration, is 10 meter per second squared, then multiplied by the height, which is 2 meters. So when we multiply everything, we get 2000 joules. So the unit of work is joules, or you can also call it Newton meter, but mostly we make use of joules in industrial and real life applications. Now let's talk about energy. Energy is very much tied to work, and in my opinion, I think energy is kind of like the predecessor of work done, because before you can do work, you must have the energy to do the work. So energy is kind of like the let's call it like the potential of work. So that is why energy is also defined here as the ability or capacity to do work. When I said energy is the ability to do work, it's also tied to a type of work known as potential energy. Now, this potential energy is kind of like the stored energy. It's the energy possessed by a body by virtue of its position. And we often deal with two major types of that, which is gravitational potential energy and elastic potential energy. Now, gravitational potential energy is when you have an object resting at, ab- at a height above the ground, and then when you release that object, it actually falls naturally. So that object has an inherent um, energy, and that energy is used to do work when it is dropped. So that is the gravitational potential energy. Then we also have elastic potential energy, kind of like when you stretch a string and you leave it at that position. Then by the time you release that string, it will naturally go back on its own to the original length of the string. It's kind of elastic potential energy. We'll talk about elastic energy in a subsequent episode, but this potential energy is also calculated by the product of the mass, the acceleration, and the height or displacement of the object from its mean position. Now, not so fast, we also have another form of potential energy known as a magnetic potential energy. So it is kind of like the energy due to magnetic force, and we'll talk about that in a subsequent video. First, let me give you a snippet on what it means. Magnetic force is the force that is due to the position, like kind of like the kind of the angular directions of the electrons or the subatomic particles in that magnetic substance. So something like iron now or steel. Now these materials, they possess an atomic property that makes them kind of attract other magnets or other ferromagnetic substances, which are substances that are highly magnetic. So now basically this magnetic force, magnetic energy, it's kind of is used to attract an object, and then that object moves a distance in the direction of the magnetic force. So that magnetic potential energy is the ability of that magnet to attract an object. Now another kind of energy is called kinetic energy. Now kinetic energy is the energy possessed by a body by virtue of its motion. Now, whereas potential energy was energy based on position, kinetic energy is based on motion. That means if an object that is moving, for example, you know what will happen when a moving car hits an object. That object in will fly away with in a particular direction. Now, that moving car is not the car itself, but the energy possessed by virtue of the motion of that car. So that is why mostly when accidents occur, people kind of get displaced, they move around kind of. So that is the reason, because these cars and moving vehicles, they have an inherent um energy, which is by the virtue of their motion. So kind of they kind of transfer some sort of that energy to the body they hit. So that object also acquires an energy which sets it out in a direction that it did not kind of expect. So there are different types of kinetic energy. For example, a student running in a race, you can also imagine when someone is running with speed and you go in the direction of that person, or maybe you extend an arm in the direction of the person running. You know how the your arm will be pushed aside with force. So it's kind of like someone pushing you. But that is not really the real cause is that the energy the student has kinetic energy, and that energy has been transferred to your arm. And that energy makes your hand move in a direction that is in the direction of the energy. Now we also have an object falling fully under gravity. It also has kinetic energy. We also have wind or air in motion has kinetic energy. Any moving body has kinetic energy, including your charges, which are subatomic concepts. Charges are basically involves the imbalance of positive and negative charges on your atomic and subatomic particles. Then you have a moving bullet or a moving hammer. So kinetic energy is kind of energy due to motion. Now let's deal with an example. An object of mass 5 kg or kilograms is moving at a constant velocity of 15 meters per second. Now calculate its kinetic energy. Now the formula for kinetic energy is given by half mv squared. That is half the product of the mass and the square of the velocity which the object is moving. So here we have half times the mass is 5 kilograms and the velocity with which is moving is 15 meters per second squared. So when we multiply everything, we get 562.5 joules. Now let's move on to power. Power is defined as the time rate of doing work. It's kind of like the derivative of energy with respect to time, if you think of it in terms of calculus. But basically what it means is that the time, rather it's kind of the work done in a unit period of time. The work done by an object in 1 second is work over time. Now so far we've talked about work, energy, power. Now let's talk about transformation and conservation of mechanical energy. The law of conservation of energy states that in an isolated or closed system, the total amount of energy is always constant, although energy may be changed from one form to another. Now, this is something that's very important for us to understand. And let's take the example where you raise a stone to a height of, um, of a particular height, and then you let the stone fall freely. Now, that stone, when you raise it up, it acquired potential energy. Then when you release the stone, it still falls down in a distance that is opposite to the in a direction opposite to the direction in which you lifted it up. Now, in our definition of work, your work taken to raise the stone to that height is equal to the work done in letting the stone fall under gravity, because in your first work you have your work, which is the weight of the stone multiplied by the height, which is if we assume positive direction of the movement for the height. Now when the stone is coming down again, it goes in a direction that's opposite, and then the height becomes negative. When we add together the work, you get 0. So that's kind of like an example of conservation of energy, because it's kind of like an example of Newton's third law of motion, which says that action and reaction are equal and opposite. If you don't know it, we will talk about that in a subsequent video on linear momentum and energy. So now there are different ways by which you can understand conservation of energy. Now I've given an example of a falling body, because when it falls, it's kind of the energy becomes conserved. It's kind of like the reaction. Falling is the reaction, and you raising it up is the action. Now let's talk about something else, about the simple pendulum. And the potential and kinetic energy of a simple pendulum is an example of conservation of energy, because when a simple pendulum consisting of a bulb attached to a string, and the other end of which is suspended from a firm support. When the pendulum swings from end to end, the energy of the system changes from potential to kinetic and vice versa. But at each stage of the swing, the total energy remains constant. So at each stage of this swing, know that when we look at the left, from left to right, at the left point A, we have the kinetic energy, which is 0, and the potential energy equals to mgh. Because when the pendulum swings upwards to the highest height, now the energy is mgh, but the kinetic energy is 0, because when it attains the highest height, it stops momentarily. That means the energy due to the velocity is 0, because when the velocity is 0, when it's up, velocity is 0, and when the velocity is 0, that means kinetic energy is 0. But when it moves on to the middle position, or the equilibrium point, you can see that the potential energy becomes 0, and then the kinetic energy becomes half mv squared, because at this middle point it has a very high velocity. And the reason why the potential energy is 0 is because that's the lowest point, so it can't go any lower than that. So if we go to the point B, we also have a reversal. Kinetic energy is 0, potential energy is mgh. Now in this case, this is helping us to demonstrate that actually at the highest point the potential energy is maximum, then at the lowest point the kinetic energy is maximum. This is the energy transformations in the motion of a simple pendulum. But some of you who are apt might be asking that what of any position in between? Now, in between these points of maximum and minimum, any other position will have a mixture of potential energy and kinetic energy. So at the point between A and C, maybe assuming that point P, you have a mixture. So some of the energy will be potential and some will be kinetic. That's similar to what happens when you throw a stone and bring it down back. So now in this video, we've talked about a couple of things. We talked about energy. We said work is a product of force and distance. We talked about energy, which is the capacity or ability to do work. We talked about potential, kinetic energy majorly. We also talked about power. Now we'll talk about transformation of energy. So hopefully you understand this concept, and I'll see you next episode.